And here's another example of how to deal with projectile motion problems. Again, we're going to try and clear the wall with a projectile shot out at 40 meters per second at some angle that's unknown. You're supposed to find that angle. The wall is 100 meters away and the wall is 10 meters tall. So you say, well, what's different about this one and the one I did earlier? And what's different here is that in the earlier one, you were supposed to find the initial velocity. You were given the angle. Here, you're given the velocity and you're supposed to find the angle. And it's a very different problem that way. So let's go ahead and get started and see how to do that. And again, how do you start a problem like this? To find the time in the air. All right, so time in the air. And here again, you have the suspicion that you're not going to be able to find it with just one equation, and you're correct. So we're going to do it in both the x and the y direction. So for the y direction, we use y equals y initial plus v initial in the y direction times time plus 1/2 gt squared. Again, realizing that, of course, it's being shot out at an angle, we're going to have to find the x and y components of the initial velocity. So the initial velocity in the x direction is going to be equal to v initial times the cosine of theta, which in this case is going to be 40 times the cosine of theta. And in the y direction, we could say v initial in the y direction is equal to v initial times the sine of theta. And of course, in this case, it's 40 times the sine of theta. Okay, and of course, the 40 means 40 meters per second. We're going to leave the units off because it makes it a lot cleaner to work with the problem. Let's plug in everything we know. Final height is going to have to be the height of the wall, which is 10 meters. Initial height is 0, plus v initial in the y direction, which is 40 times the sine of theta, 40 sine of theta, times t minus 4.9 t squared. And realizing here, of course, we don't know the angle, we don't know t, so we have two unknowns in this equation. We cannot solve it for t. So what we're going to do now is use the x equation, or the horizontal equation, so time in the air in the x direction. So we have x is equal to v initial in the x direction times time. And v initial in the x direction is right here, so we have x is equal to 40 times the cosine of theta times t. And of course, we do know the x distance. We know that's equal to 100. So 100 is equal to 40 times the cosine of theta times t. Divide both sides by 100, or 2.5 equals the cosine of theta times t. So here we realize we have two equations, two unknowns. I can go ahead and solve that equation for t and plug it in here. So we'll do that. So t is equal to 2.5 divided by the cosine of theta, and I'm going to plug that in here and in there. All right, let's do that. So our equation now becomes 10 is equal to 40 times the sine of theta times t, which is 2.5 divided by the cosine of theta, minus 4.9 times 2.5 divided by the cosine of theta, quantity squared. Okay, I can simplify that a little bit. I can multiply this times this, and the sine divided by cosine is the tangent. So we have 10 is equal to 100 times the tangent of theta minus, okay, let's work that out a little bit. We have 2.5, we square that, and we'll multiply that times 4.9. So that gives me 30.625, so minus 30.625 times 1 over the cosine squared. 1 over the cosine squared, that's actually equal to the secant squared. So we can write this as the secant squared of theta. Okay, now we still have a problem. We have the tangent of theta here, and we have the secant square of theta there. But then I remember there's another identity. Let's write it down over here. The secant square of theta is equal to 1 plus the tangent square of theta. We can replace this by that and plug it in here. So this becomes 10 equals 100 times the tangent of theta minus 30.625 times 1 plus the tangent square of theta. And I can simplify this a little bit more. I can multiply this times the 1 and move it over to the other side and add it to the left side. So this becomes 40. And you know what? I'm going to leave off the 6.25. We don't need to be that accurate. So we'll just say, okay, 30. So we'll get rid of that. 30 times 1, minus 30 times 1 is minus 30. Move it to the left side. That becomes plus 30. Plus 10 is plus 40. Equals 100 times the tangent of theta and that becomes now minus 30 times the tangent square of theta. And then I begin to realize something. I have a quadratic equation, but instead of a quadratic equation like x or y, I have a quadratic equation in the tangent of theta. See, notice I have a term, a constant term here, tangent theta of the first power, tangent square of theta. So I'm going to move everything over to one side and write this as 0 is equal to, and I'm going to write this term first, minus 30 times the tangent square of theta, plus 100 times the tangent of theta. And when I move the 40 over, it becomes a minus 40. Of course, I don't like negatives in front of the square term, so I'm going to multiply both sides by -1 and write it over here. So I'm going to come over here. And this is going to be 0 is equal to a positive 30 tangent square of theta minus 100 tangent of theta, and that would be plus 40. So now I'm going to make a substitution. That's a typical math trick. Instead of tangent of theta, I'm going to call it z, some other variable. So let z equals the tangent of theta. If I do that and substitute, I get 0 is equal to 30z squared minus 100z plus 40. And now I'm going to solve this equation and then later plug in the tangent of theta again. So using the quadratic formula, that z is equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a. And of course, this here is a, this here is b, and this here is c. Plugging that in, I get z is equal to minus b, which is 100, plus or minus the square root of b squared, which is 10,000, minus 4 times a, which is 30, times c, which is 40. All divided by 2a, 2 times 30 is 60. All right, let's see if I did this right, because if this becomes a negative number, I can't solve that. So 30 times 40 times 4. And that's negative, that's minus 4,800, subtract that from 10,000. So that looks good, that's a positive 5,200, and I take the square root of that, and it's 72. So we have z is equal to 100 plus or minus 72 divided by 60. That means I have two plausible answers. Does that make sense? Well, we'll see in just a moment. So it's 172 divided by 60, 172 divided by 60 equals. So we have z is equal to 2.87, or z is equal to, when I take the negative 100 minus 72 divided by 60, and I get 0.47. And actually that makes sense. And we'll see in just a moment why. I'm going to substitute back to tangent of theta. So that means that the tangent of theta is equal to 2.87, or the tangent of theta is equal to 0.47. That means I can come up with two different angles, which means there are two different angles which will allow the projectile to clear the wall, which means probably anything between those two angles will allow the projectile to go over the wall. Those are the limiting values. So let's find theta 1, which is equal to the arctangent of 2.87. So let's find the arctangent of 2.87. Arctangent is 70.8 degrees. So theta 1 is equal to 70.8 degrees. And theta 2 is equal to the arctangent of 0.47. 0.47. Arctangent is 25.2 degrees. So theta sub 2 is equal to 25.2 degrees, which means if the projectile is shot out at 40 meters per second, at an angle of, as a minimum, 25.2 degrees, it will clear the wall, and as a maximum, 70.8 degrees. Because if you make it greater than 70.8 or less than 25.2, it will fall short and hit the wall or hit the ground before the wall. But anything between those two angles, the projectile will actually go over the wall. And that's how you do that problem.